Now I want to look at the question of existence and uniqueness, which, if you took linear algebra, you probably have studied that a lot for linear systems. So here we've got the typical setup for an initial value problem. It looks like this, right? You've got an unknown function x prime x, you've got an unknown function x of t, and you've got a differential equation x prime equals and then some stuff involving x and t. And you've got an initial condition, x of some time, usually 0 but maybe not, equals some value. Then the question is, well, usually the question we've been posing and the question we've been wondering about is, can we solve it? Can we write down the solution? But there's a kind of different mathematical question that one can ask, which is, does a solution exist? And one way to think about that kind of question, kind of graphically, so this is not a phased line diagram or anything like that, it's just a plain old graph. In the tx plane, where you might graph x of t if x of t were a solution, you know you've got, I mean, t equals t naught somewhere on this axis, and you've got x equals x naught, and your initial condition is a point that you want your graph to pass through. It's a point in the xt plane that you want your graph to pass through. And your question, does a solution exist, is basically the question, does there exist a curve running through here, which is the graph of a function x of t that satisfies this, basically, and satisfies this. You can see that in the picture. So that's kind of the question is, given this little starting dot here, is there a way to extend a line through this dot so that it's the graph of a function that satisfies the differential equation, x prime equals whatever is over here? So that is the question. And here is the answer. So to explain the answer, you need to really think about what kind of function f of x and t is. F of x and t is a function of two variables, x and t, and it outputs one number. Given any two inputs, x and t, it outputs one number. So it's a function on this space here. At every point in this function f of x and t, at every point here, it gives you a number, right? It gives you different numbers at all of these different points here. If there is a rectangle that contains your initial t naught comma x naught, your initial condition point, in the inside of the rectangle, so not on the edge, not on the boundary, but in the inside of the rectangle, and with the property that in that rectangle, f of x and t is nice. It's a nice function. And I will let you look at the theorem in the book if you're interested in what nice exactly means. It has to do with the derivatives of f with respect to x or t, and whether those are continuous functions. But let me just summarize it as nice. If it is a nice enough function on the inside of a rectangle, which contains the point, your initial condition point on the inside of it, then yes. So if f of x and t is nice inside some rectangle here, then yes. Yes, a solution exists. So it's possible to extend this. Now, it's not guaranteed that the solution exists throughout the entire rectangle in which f is nice. It might cut off somewhere, like it might only exist in this smaller region. You know, maybe it stops there. And that's it. But that's fine. You're guaranteed at least that there's some positive distance to the left and to the right of t naught so that your solution exists. Okay, so don't worry too much about the details of this. Mainly what I want you to get out of it is a kind of a philosophical point, which is when you're approaching a differential equation, and the function here is nice, which it usually is in most cases that you actually look at, when you're looking at a differential equation and you're asking yourself, oh, how do I solve this? What's the solution? Knowing this fact that a solution exists kind of changes the way you're thinking about what you're doing. It's not a matter of, can I find a solution? If I find one, then I'll know it exists. No, it's a matter of, it is mathematically proven that a solution exists. And my task is to find one. If I can't find one, that doesn't mean it's not there. We know it's there. But the difficulty is just writing it down. So I guess the philosophical point that I'm talking about is that often the difficulty with hard differential equations to solve is a difficulty in writing down the solution, not in gaining the knowledge that there is a solution, at least for these kinds of differential equations that we're looking at. So another interesting thing you get out of the theorem, so here what I'm telling you is a theorem. When I say if this is true, then yes, that's something that requires proof, but that just is something you might do in an advanced differential equations course, not an introductory one like this one. But one other nice thing that comes out of the theorem, or that is usually included in the same theorem, is uniqueness. So not only are we guaranteed a solution exists in some little window around T naught when f is nice, we are also guaranteed uniqueness. So, and it's unique. So that means there's not like more than one possibility. There's exactly one. So you couldn't have multiple competing possibilities for what the solution is. There's one solution, there is one solution, and there's only one, and your goal is to find it sometimes. We've also seen that sometimes you don't really care about finding it, right? Like with autonomous differential equations, we've just been analyzing them without finding the solution.